joined Sun Oil Company, and he was in Pennsylvania, where he achieved the level of senior scientist. Let's see, after that, that's when he joined the University of Oklahoma. And he's been there for, I guess, about 7 years?
8 years.
8 years. And his projects at University of Oklahoma included the selected catalytic reduction of NO for automobile catalysts, as well as production of syngas from CO2 or forming of methane. And he's also done some work on basic zeolites loaded with metals for reforming reactions. Today he's going to present on the selective production of single-walled nanotubes using catalysts. So please welcome Dr. Daniel Resasco.
Thank you, Gary. Thank you very much for the invitation, Gary. Thank you, Bert. I have to say that when I met Bert the other day in Houston, he told me he was very happy with Gary, and they sent me as many of those as you have. He said, I don't have as many as Gary. All right, what I'd like to talk today is on our efforts to produce carbon nanotube with single wall by a catalytic decomposition of carbon monoxide. What I'd like to discuss briefly, how do we make it, the catalytic production, the characterization both of the tubes and the characterization of the catalyst that allows us to explain, or at least to have an idea how these catalysts work and why they're better than most of the catalysts that have been tested in the literature, reported in the literature. As you all know, the single-wall nanotubes are a cousin, at least formally, of the well-known buckyball. If you start extending the buckyball, you end up with structures like this that are being called nanotubes. And of course, that has to be differentiated. What is a single-wall nanotube? That was the focus of our effort to produce this type of carbon structure, versus the multi-wall nanotubes, which you can make it as nice as this, as these guys are making it here, or in most cases you make things like that that are not as nice looking as these ones, and there are lots of defects. So our main effort was to produce single-wall nanotubes. Let me very briefly tell you a little bit about the properties of single-wall nanotubes and the potential applications. It has very unique mechanical properties. The strength of this material has been calculated to be between 200 or 300 times that of steel, the tensile strength. So the possibilities to make extremely strong and extremely light materials are tremendous. Electrical properties are also very interesting, depending on the helicity of this material, how they actually fall into a tube. They can be metallic or they can be semiconductor. A lot of people, thank you, working on possibilities of using these single-wall nanotubes as absorbent for the storage of gases. Has been proposed that they can be used as sensors if they are chemically modified or chemically attached with a sensing tip. They can be used as sensors. And all of this in the really small scale of 1 nanometer diameter and a few microns long. So there is a lot of interest on producing nanotube composites. There has been a recent report in Science, and the nanotubes can be put into a polymer, into matrix polymer, something that a lot of people are working even here to make a material that it can be flexible and strong with fantastic properties. Very interesting. Nowadays, last week, IBM came up with a big splash of the production of nanocircuits that can be selectively removing the metallic and leaving there the semiconducting nanotubes to form the first nanotransistor, which has been proposed over here. as I said before, depending on the helicity of the tube, you can have something that is metallic or semiconducting. And, well, certainly the potential to work on nanoelectronics is there. Another application that is interesting to mention is the use as very thin, extremely precise for nano manipulation, either for sensing different surfaces or nanolithography, or even to do nanochemistry on a catalytic surface. And probably the application that's going to have a commercial result very soon, or the soonest, is the field of field emission for the production of flat panel displays. Since nanotubes have a high aspect ratio, with low voltage, you can have a very high emission. So we can have materials that are flat panels with very low voltage application. You can have very high brightness and effectiveness. Okay, the interesting thing is that all these fantastic applications, all these potentially fantastic applications, are faced with a reality that is, so far, the production of single-wall nanotubes has been limited to micrograms, very small, or milligrams, very small quantities that make all these potential applications very difficult to realize. The two methods that people have used more frequently are the arc discharge or the laser ablation, that they result in nanotubes, single-wall nanotubes of very high quality. However, the amount, the yields of that are really low. I have this one here. The method that we have developed, that we even have a commercial name for that. So far we only have a company that has been formed, and we have a registered mark for our process. It's a catalytic one that is relatively simple. We have a feed of pure carbon monoxide that we operate at a relatively low pressure, from 1 to 5 atmospheres of pure CO, and a relatively low temperature range compared to what most people are using, between 700 and 900 degrees C, and a catalyst that is our unique formulation. We have a patent for that. That produces a very high, relatively high yield of single-wall nanotubes, and most importantly, very high selectivity when operated in the right conditions. So we have some patents for that, and we have just formed a company that the goal for that company will be production of single-wall nanotubes of high quality at a relatively low cost. This is our estimated cost, which can be compared to $500 to $1,000 per gram. That is the cost today. Okay, let me really briefly tell you about the catalyst preparation. We use a silica support, and I will describe later why we have chosen that support. So, we prepare by incipient wetness impregnation with cobalt, nitrate, and ammonium heptamolybdate. After that, we decompose those salts on the surface to produce a cobalt moly mixture with a first calcination at 400 degrees, followed by reduction in hydrogen at 500 degrees, and then to heat to the reaction temperature, which could be 700, 800, or 900 degrees in helium. Okay, all these steps are extremely important. Okay, if you change one of these steps, selectivity drops tremendously. So a typical single-wall nanotube appear in bundles like this. This will be one that has been produced by laser ablation at Rice University. And you can see that when you look at the bundle, and if you're lucky enough that the TEM actually captures the tubes coming up to you, you can actually see them coming. And this is the one that we prepare without a method at 700 degrees. And we see we are also able to find something that looks very similar to that. And these are our single-wall nanotubes, again bunched in bundles like that. This is an SEM picture just to show you Now we produce these carbon nanotubes. They appear in bundles. Each of those will be a bundle. And of course, you have the silica that after we produce it, we need to remove it. We have found a way to remove the silica very easily by bleaching with a basic solution of sodium hydroxide. So we remove in that attack essentially 99% of the silica, and then with a subsequent acid attack, we remove the cobalt and the moly. So here we have an AFM study where you can see the length of the tubes. They are normally 2 to 5 microns long, and we have around, well, let's say less than 10 nanometers in diameter. So we have only a few nanometers in that bundle. One of the important things that we need to consider when we do this development is a selectivity. That's something that is normally not done in the literature because most of the people who are involved in these single nanotubes are not people that are used to work in catalysis. So they report they have been successful in producing single wall nanotubes, but the question is single wall nanotubes and what else? What is your selectivity? So we spend a lot of time in developing methods to measure the selectivity of the carbon deposits. Okay? For example, you can see that in addition to the single wall nanotubes, you produce other forms of carbon. So one of the techniques that has been used to characterize the nanotubes is Raman spectroscopy. Raman spectroscopy has 3 regions, one of high frequency, which is typical of the graphite type tangential modes of vibration, in the region of 1580 to 1560. And okay, that appears on all well-structured graphite deposits. In the intermediate frequency, there is a very important D band that measures the disordered carbon. So a very nice way to look at selectivity, how much of that is ordered, how much is forming either microcrystalline graphite or fibers, is that the D band. And then for single wall nanotubes, the very important region of the low frequency, that corresponds to the breathing mode of the tube, the vibration in and out around the diameter. This technique not only allows you to see whether you're producing single wall nanotubes, but also, since the frequency of vibration depends inversely with the diameter of the tube, allows you to see whether you're producing tubes of one diameter or another, or you're actually producing a distribution. Here we have one of the spectrum of our catalyst, of our nanotubes, and you can clearly see that you have the well-ordered G-band there, a small fraction of disordered carbon. This is as prepared before any purification, even without removing the catalyst. This is the Raman we obtained, and you see the breathing mode shows you a very sharp, very intense line indicating the presence of single wall nanotubes. Another method that we use from the very beginning is temperature programmed oxidation of single wall nanotubes. When you have the single wall nanotubes on the catalyst and you pass 4% oxygen and helium, the oxidation of the carbon begins, and depending on the different type of carbons, the combustion takes place at different temperatures. So for example, if we look at a graphitic one, so that will burn at very high temperatures. If we have a catalyst like cobalt moly with a ratio of 1 to 2 that produces a high selectivity to our single wall nanotubes, we observe the burning of carbon around 500 or 510 degrees C, which correspond very much as the tubes of rice purified. Okay, the way we did this is we mix those tubes of rice with our catalyst. So since the TPO is a catalytic process, we burn it in the presence of the catalyst, and we observe a very nice correspondence between when the nanotubes burn and when the tubes of rice burn. Now, with this technique, we have been able to study different compositions of cobalt and moly, and we found that when we have moly alone, you don't form under those conditions, there is 700 degrees C, any ordered carbon. neither by Raman or by TPO, we observe the formation of any nanotubes. When we have cobalt alone on silica, cobalt is very active, but it's very unselective for carbon nanotubes. So it forms multi-wall nanotubes and forms graphite. However, when we have cobalt moly, we observe a very nice synergism that shows that, for example, when you have a ratio of cobalt to moly 1 to 2, we observe the peak that we showed before that corresponds to single-wall nanotubes. If we increase the amount of cobalt, so we have now cobalt in excess, we have some single-wall nanotubes, but now a large amount of this peak, that essentially corresponds to fibers, graphitic, small graphitic particles, which we call the non-selective catalyst. If you do Raman on that, this one correlates very nicely with this. You don't observe any ordered carbon here in the deposition on the pure moly. The cobalt is very unselective. It forms as much ordered carbon as disordered carbon. The cobalt moly 2 to 1, you see start forming a lot more disordered carbon. But when you have the cobalt moly 1 to 2, that one decreases and the ordered G band of the nanotubes increases. And TEM clearly shows the same behavior. Moly alone doesn't show any ordered carbon depositions. Cobalt alone is very unselective, forms a lot of this multi-wall and a lot of this graphitic and fiber carbon. But the cobalt moly forms a high density of single-wall nanotubes. Temperature, that's a very interesting parameter. For example, as we increase the temperature, the amount of carbon that we obtain decreases. However, when you go to very low temperatures, such as 600 degrees C, the TPO shows you that in addition to some single-wall nanotubes, you start producing something that burns a much higher temperature, which is corresponding to the fibers, multi-wall nanotubes, and TEM show a good correspondence with that. You see that 600 degrees, you observe those irregular fibers. But if you do the reaction at higher temperature, 800 degrees C, the selectivity towards single-wall nanotubes clearly increases. Again, if we do Raman, we can see the one that we did at much lower temperature, 600 degrees, resulted in a much lower selectivity, as indicated by this band of disordered carbon. Okay, so let me summarize what I have shown so far. We have found that cobalt moly is much better than cobalt alone or moly alone. And when you change the ratio of cobalt to moly, you have a drastic effect on selectivity. So we found the maximum selectivity when we have low cobalt to moly ratio. So let's try to explain that behavior in terms of the role of the catalyst. Why is this happening? So for that we have a big effort on characterization of both cobalt and moly by FTIR, UV visible spectroscopy, X-ray absorption, XAFS, and XPS. So with this we've been trying to understand how the catalyst is before the reaction, that is in the calcine step, right after the reaction, the reduce step. As I said before, if you do not reduce this catalyst, it's not selective. So that reduction, pre-reduction step is extremely important. And what happens during reaction? How cobalt and moly are modified during reaction. Okay, let's look at the calcine catalyst. The first thing that we look at is the UV visible spectroscopy. If we have a catalyst of pure cobalt on silica, okay, this is the calcine state. What you expect to find here is cobalt 304, cobalt oxide, and this is a typical spectrum of cobalt 304. When you have cobalt moly 3 to 4, that catalyst will be unselected. If anything that is above 1 to 2 in cobalt to moly is unselected. And you can see that that one has bands here that correspond to both. Those that appear in pure cobalt, but also this one that only appears in cobalt to on the low cobalt to moly ratio. If we compare that with the references, we can see that this one looks exactly the same as the cobalt 304, indicating that in the pure cobalt on silica you have cobalt 304 oxide. But when you look at cobalt molybdate has the octahedral type band here that corresponds exactly to this band that we observe in the selective catalyst. Okay, so first thing we start saying is that when we have the selective catalyst, the cobalt is in a surrounding that looks very much like cobalt molybdate. Okay, let's continue with that. So if you look at the EXAFS data, again from the calcined catalyst, and try to understand the state of cobalt, we see that the unselective catalyst, in this case, will be the cobalt moly 221, and is the blue curve here, is almost exactly the same as the reference cobalt 304, confirming what we said before. The unselective catalyst, that is when you have more cobalt than the moly can stabilize, it acts as if it were alone. Okay, so cobalt, when it's calcined, forms cobalt 304. On the other hand, the selective catalyst, it will have a cobalt molybdate-like structure. We call it cobalt molybdate-like structure because when we try to compare or do a fitting of this data with cobalt molybdate, we don't observe bulk cobalt molybdate. So we start making the picture now. If you have the cobalt unmodified, will form cobalt 304. If it's in the presence of moly, with excess moly, it's going to start forming a cobalt molybdate-like structure. Okay, let's look at the state of moly. Okay, UV visible spectroscopy is a very nice technique to study molybdenum oxide because depending on the state of dispersion of molybdenum oxide, you observe a different band. It's a method that Enrique Iglesias had developed to try to calculate the size of the molybdenum oxide clusters, and he observed, as the same as we, as the molybdenum oxide cluster increases in size, the size of the band gap decreases. And from this one you can observe really nice correlation that as you increase the molybdenum content, the energy band decreases. So by the analysis of this on your catalyst, you can have an estimate of how big the molybdenum oxide domains are. And we can see here, again, a nice correlation between what we observed before and this heptamolybdate type. So by comparison of this spectra, we can say that our molybdenum oxide is in a relatively high state of dispersion. That is, we don't have any molybdenum 3 oxide, and rather will be something between molybdenum 3 oxide and heptamolybdate. Okay, now let's move to the reduced catalyst. Remember that we first calcined, and we had this oxidized mixture of cobalt and moly. The good catalyst would be cobalt molybdate-like, with the molybdenum oxide in a relatively high state of dispersion. Now, before the reaction, we reduce it, because if we don't reduce it, the catalyst is totally unselective. So let's try to understand how are the catalysts before the reaction. So if you use NO as a probe in infrared spectroscopy, you can see the NO absorbs and has the two typical dual bands of the symmetric and asymmetric or antisymmetric vibration. And so it's very easy to determine when you see these two bands that this is NO absorbed and moly, and when you see these two bands that this is NO absorbed and cobalt. So when you have the cobalt moly catalyst 1 to 2, you can see that essentially all the cobalt is there while the moly is reduced very much. So this is a demonstration that actually the cobalt is partially covering the moly, and as you increase the amount of cobalt, this is what happens. With cobalt moly 1 to 3, there is still a lot of moly available. As you start adding more and more cobalt, this peak that corresponds to moly decreases. Okay, so the picture that we have is that the moly oxide becomes covered by cobalt. It forms a cobalt molybdate. When you have too much cobalt that you actually cover all the molybdate, you observe a clear shift between here and there, and that's exactly the same position that we observed before for pure cobalt. So moly is able to stabilize cobalt up to a certain level. After that, cobalt starts becoming as cobalt oxide, separate phase. Okay, let's look at the state of cobalt before the reaction in the reduced state. Does cobalt get reduced? We reduce at 500 degrees C. This technique, ZANES, is a very clear indication that, let's say, this is metallic cobalt. When you have cobalt alone, cobalt can get reduced at 500 degrees. However, if cobalt is in contact with moly, that cobalt molybdate is more difficult to reduce. So a large fraction of cobalt resists reduction at 500 degrees. So just before the reaction, what we have is a catalyst in which molybdenum is partially reduced, but cobalt is still partially reduced. We don't have metallic cobalt if we have the selective catalyst. Here is clearly demonstrated in the Fourier transform of the X-halves. As you increase the amount of cobalt, that is, you start losing selectivity, you can see that more and more of the cobalt is metallic. Okay, this is the band length that corresponds to metallic cobalt. This is the cobalt-oxygen bond. So you see that as you start having more and more cobalt, that cobalt becomes or detached, let's say, unstabilized by the moly, and that one can get reduced very easily. Now, XPS corresponds very nicely with this. So as you start increasing the cobalt to moly ratio, a larger fraction of cobalt gets reduced just before the reaction. If you have a selected catalyst, most of the cobalt is in the non-metallic state. Okay, how about moly? Well, moly doesn't really matter where you have the selective catalyst or the unselective catalyst. Moly looks very much like heptamolybdate. So how can we explain that the cobalt, the chemistry of the cobalt strongly depends on the amount of cobalt moly, but the chemistry of the moly doesn't? So one explanation is what Sinfeld used years ago with the ruthenium copper, when he observed exactly the same behavior. If you have a little cake in which the molybdenum oxide is forming an oxide layer, and you only decorate the top of that with cobalt, cobalt will be very much affected by moly, but moly will not be very much affected by cobalt. And more cobalt that you put in, you're going to go away, it's not going to modify the molybdenum. So from the molybdenum point of view, things don't change in the selective and unselective catalyst. But from the cobalt point of view, it changed drastically. Okay, just before the reaction, what happened with the moly? The moly is in the form, as we said before, of a heptamolybdate type. Again, in correspondence with that, we can compare the X-half spectra for the molybdenum trioxide. That should have a large peak here that is not there for the catalyst. That again corresponds very well with the high state of dispersion of moly. And XPS for that shows that we have a combination of moly 4 plus and moly 6 plus. Before the reduction, that is after calcination, all the moly is in the 6 plus. After the reduction, the cobalt still remains unreduced, but the moly reduces a little bit to cobalt 4 plus. And that must be the important point, because if that doesn't happen, the catalyst is not selected. That is, we need the reduction. The reduction doesn't reduce the cobalt, but does something to moly. And at the end, I'll have the explanation for that. Okay, important part here. This is the critical and most important consideration. When we look at the spent catalyst, what happened with moly? Moly, it was before the reaction, like this. We said that was a moly oxide partially reduced, a mixture of moly 6 and moly 4 plus. Now, after the reaction, this one changed drastically. What happened? What would we have converted this into? Anybody want to guess? Moly carbide. The molybdenum has been converted into moly carbide. If we look at the X-halves of moly carbide, is the red, the black one here, correspond exactly to the catalyst after reaction. So when we do that before reduction, we expose that to the CO, moly carbide is not formed. So it seems that the formation of those oxygen vacancies, moly 4 plus, are necessary to let the CO attack and form very quickly the moly carbide. And again, the sayings correspond to that idea very closely. So let me see if okay, before I go with that. What happened with cobalt? Before reaction, I said cobalt has not being reduced. Due to the interaction with the moly, it resists the reduction. The moly underneath gets partially reduced. During reaction, the moly gets formed into carbide, moly carbide. The cobalt, during the reaction, gets reduced. 10, 30 minutes after reaction, it starts looking very much like cobalt foil. And at the same time, you can see that as a function of time, the cobalt, which was mostly oxidized, start getting reduced and the particles grow in size. Okay, let me, before I put the cartoon of this picture, let me review this. We have selective or non-selective catalysts. This one is those in which the cobalt to moly ratio is low. Okay, all of the cobalt is stabilized by moly. Before the reaction, all the moly is in the 6+ state. After it gets reduced, we have a mixture of 6 and 4. This is necessary because during the reaction, that moly becomes moly carbide. In the selective catalyst, the cobalt is in the cobalt molybdate-like, that is stabilized by moly. When it gets reduced, it's not affected by the reduction. It's only the moly that is affected by the reduction. During reaction, that one starts getting reduced and forms cobalt metal. What happens in non-selective? The non-selective, again, you start with moly in the 6+, but cobalt is not in the cobalt molybdate. Cobalt is like cobalt oxide. That cobalt oxide can get reduced before reaction and remains reduced after the reaction with the formation of nanotubes. This one does form carbide. But then the important point is this one here, right? So I have this cartoon to explain this is the idea why this is happening the way it's happening. We start in the selective catalyst with most of the cobalt and moly in this form. Moly forming a well-dispersed molybdenum heptamolybdate type. A small, not big chunk of moly of 3, but rather small polymeric forms of moly oxide. Cobalt is on top of that, forming a molybdate type structure. Okay, if you look at with UV visible, which only looks at the surrounding of that, or SANS, that looks very much as cobalt molybdate. If you do with XAS, that's going to look for a bulk of cobalt molybdate. It doesn't look like cobalt molybdate. If we have excess cobalt, that excess cobalt will be oxide. If we reduce it before the reaction, that would become metallic. What happened during reaction? Of course, this one will be the typical behavior of cobalt alone. It will form fibers, it will form multi-wall nanotubes, it will be encapsulated by graphite. That's what we're trying to avoid. But what happened here? The molybdenum oxide gets converted to molybdenum carbide. When molybdenum carbide now destroys this cobalt molybdate, now CO can reduce this. So in this moment, we have this nascent, very small cluster of cobalt, which were essentially atomically dispersed. In the non-reducible state, all of a sudden, they are under reaction conditions, high temperature in the presence of CO. They are ready to form nanotubes, but they are so small that they don't form these fibers of nanotube, but rather they form the typical single-wall nanotubes. Okay? All right. We can compare that with the method that has been developed recently at Rice, which is called a HIPCO. In this method, they produce single-wall nanotube. By this method, they have a 1200 degrees C, an injection of carbon monoxide, and iron pentacarbonyl. What happened there is that iron carbonyl decomposes, and in this flow, those particles grow. Okay, so they grow in the presence of CO. This is similar conceptually to what we have there, that you send in the presence of CO very small clusters. But it's a big difference in the fate of the particles in their case and in our case. We have still the solid there that limit the growth. So we have the chance of a better control of the fate of those clusters. And as a result, I like to show you this comparison here. This is the low frequency region that shows the vibration, breathing mode vibration. In our case, that you see, remember as I said before, the higher the wave number, the smaller the diameter. So we have a relatively narrow distribution because that one is governed by the size of the metallic clusters that they have been grown right there, that under reaction conditions. While this is what the product from rice looks like. So you can see that they have a much broader distribution of diameters than we do here. Now, what happens if we increase the temperature? If we increase the temperature, we're going to increase the rate of sintering. So as a result, we should observe a shift toward lower frequencies. And that's what happened when the temperature increases. Now you have more of the distribution of sites, but it's kind of bimodal. Here we have this narrow one here that is more or less the same as this one. And we already have this shoulder here, so these are a little bit larger nanotubes. When the temperature increases, we have more of this. Okay, so to summarize this, I'd like to say that we have developed a methodology to optimize in the selectivity, mostly focused on the selective single wall nanotube. And this was done on a dual characterization, not only the tubes to see what we're producing, but also a detailed characterization of the catalyst to understand how this works. And we have found a synergism between cobalt and moly. Cobalt alone is unselective, even though it's very active. Moly alone is inactive. The role of cobalt there will be the activation of CO. That's the active ingredient, cobalt. And the role of moly is to the stabilization of cobalt in a non-reduced state just before the reaction when it's needed to be in the metallic state. We produce a relatively narrow distribution of diameters, and we can, at least the beginning, this is just very recent, we can in principle control the diameter of the nanotubes. To finish, I'd like to acknowledge the members of the group, Walter Alvarez and Armando Bornia. These are postdocs, and these are the 4 students who have been working, Lucky Tillana, Leo Balsano, Jose Herrera, and Francisco Pompeo. And I thank you for your attention.
Any questions?
Matter of interest, we were discussing earlier, you seem to have chosen a typical hydrodesulfurization catalyst. Have you looked at nickel mollies?
Yes,
Tungstens?
we look at all of them.
And how do they compare?
They form nanotubes, but not as selective as cobalt moly.
Cobalt is the best.
Cobalt moly is it.
But the others do.
The others do. The others do, but at any ratio that we tested, they still produce multi-wall nanotubes. There is a slight difference with the HDS catalyst. They are the preferred support is alumina. The problem with alumina is that it interacts very nicely with cobalt. So actually, you don't have there such a strong interaction. In the alumina, you don't have the cobalt molybdate formation because cobalt tends to interact with alumina more strongly than with moly. So silica was the best, right?
But you have tried the others, not just one.
Yes, we have all the.
I'll ask something else. In the introduction, you mentioned you worked on reforming catalysts long ago.
No, this is methane reforming. That's very recent. Yes.
With nickel catalysts, you also get these spider-like, thread-like.
Oh, yes.
Are they in fact nanotubes? I've never thought of this.
Well, I don't know. They are some of them. They're hollow.
But they look just like these threads.
It looks, yeah, very much the same. Actually, when I worked for Sanoil, my project there was the hydrogenation of isobutane, and the catalyst they were working was based on nickel. So if we didn't passivate, they will form these fibers a lot. So that was my first nanotube.
In old literature, you get these pictures.
Yes.
No one they mention the word nanotube.
Well, before, yeah, I think.
They didn't realize it all.
Well, it was a moment that it was some discussion whether they're talking about the same thing with different names. Actually, multi-wall nanotubes, perfect multi-wall nanotubes, they are clearly defined. They are tubes, concentric tubes, one on top of the other. Okay, those are definitely multi-wall nanotubes. Then you have fibers that are just graphite planes forming like that. And then as you start getting into a muddy area, between saying that these are multi-wall nanotubes or not. The ones that are actually hollow, but they don't have a perfect structure, but they just have this like herringbone type structure, or like palm trees type. So yeah, people have seen those for a long time. In the 70s already. And actually at that moment, we want to get rid of those because that will destroy. They are so strong, they will actually destroy the pellet, right? And increase the pressure drop in the reactor. And now they're the good guys.
Am I right in saying that you need something like carbon monoxide to reduce the unreduced cobalt? That forms a carbide, and then that initiates the whole process. What would happen if you used something like methane as a feedstock?
We have. That doesn't show. It doesn't give the selectivity.
So it's specific.
It's specific.
Carbon
Yeah,
monoxide.
yeah. It's this combination of reduction in place
Yeah,
that result. Right,
that's the driving force.
right.
Suppose you
Seems to
use
be.
hydrogen in the feed. Does that help?
We tried that. We didn't observe any major difference. Yeah, we have tried that, but no difference.
You tried hydrogen in CO? Put a hydrogen there?
Yeah, that's what he was
Oh,
asking.
sorry,
Yes.
no, hydrogen.
Yeah, yeah, hydrogen CO. Hydrogen CO. Oh, you were talking about methane and CO?
No, hydrogen you say in CO. You must have some sort of amorphous carbon there as well.
Yes.
So the hydrogen would certainly help to remove that.
Well, it's not a big problem because after the reaction, we do burning at low temperature.
It's like a TPO or something.
Right. So you saw that the first part is all the amorphous or all the amorphous or oxygen containing, because sometimes even without oxygen you can do a TPD in helium and you absorb CO. So some of the amorphous or functionalized carbon remains there, but not the tubes. So that's not a big problem. You can get rid of the amorphous carbon, which is always small, but by burning.
Are there any other ways of stabilizing small CO oxide clusters?
Cobalt?
Without using cobalt, without using molybdenum?
Well, yes, you can have cobalt aluminate, but that will never get reduced.
Okay.
So the nice thing of the cobalt moly is that it stabilizes cobalt in the oxide state, but then gets reduced in the right moment. If the stabilization is too strong, it doesn't get reduced. It doesn't form any carbon.
Promoters,
What?
even promoters, alkali metals.
We haven't tried. Well, you say cobalt alumina with alkali? No, we haven't tried that.